we can do as much as possible. We're done. Um, I'm going to give you a little bit of, I'm going to give you some graph paper again. And if you want an index card or survival card, you can have one. And so so as I had mentioned, I I taped a video that goes over some of the problems on that review. So there's the announcement for that. I sent an email also yesterday about that. So that's on the Blackboard page, right? So if you go to the Blackboard page, um, right there under sample tests, there's of course there's the sample test and the answers, and then there's the review. So I mentioned on that review video, I mentioned as I was going through some of the problems, I mentioned some of the things that you might want to include on your survival card, some of the important formulas, right? That you might want to include on the survival card. I mean, you can include what you like, but it was just things that were occurring to me that I might put on a survival card while I was working at while I was working those while I was working through those different types of review problems. So this doesn't cover every problem, right? On the review, it's just selected problems. I don't know if it's even half the problems, but selected problems from the review, and a couple of them at the end today because it's some of the things that we're talking about today. The questions from the review, I saved those for today. There is, while I'm thinking about it, there is here's the review answer key, and on this problem number 3, which I did go over on that video, but one of the things that you were asked to find, so you have to compute a resultant vector here, just a sum of two vectors. Then it says find the direction and magnitude of the resultant vector. So there's the as it turns out, so you can watch on the video. As it turns out, there's the resultant force vector. You have two forces acting on an object here. So there's the resultant force vector. There it is in exact form. Here it is in a decimal approximation form. And I did compute the magnitude of that, but I forgot to compute the direction on the answer sheet. So this part is not on the answer sheet. This is computing the direction, but that is on the video. Okay. All right. So it's just computing the direction of a vector is all you're doing. And there's other problems on the test review about computing the direction of a vector. And so, but anyway, I did include that on the video, even though it's not on the answer sheet. So if you were looking on the answer sheet and wondering what happened to the direction, I just forgot to put it on the answer key, but it is on the video. I think it turns out to be this, unless I made some sort of computational mistake, which is possible on this problem and other problems as well. I can make mistakes like everyone. Okay, so we're going to look at a little bit later on here a couple of problems at the end here that deal with planes, I think. And so I think that's problems. I it's problems 11 and 12. Yes. Okay. So because those are things that we're talking about. Those are things that we're going to discuss today. Okay, now as far as the let me go back to the homework here for a moment and say something about the homework. So this homework is due this evening. And so this is like 8 or 10 problems. So this is pretty short. And I think the problems are mostly straightforward. They're just mostly cross product problems and maybe applications of cross product. So it's mostly computing cross products. And then this one is scheduled to be due on the day of the test. So now this is about lines and planes in space. And so that is a key homework. But there are some problems on there that they're good problems, but they're a little bit non-standard problems. So they require a little bit maybe more thought. And so I don't want you to spend all your time trying to figure out the solutions to those problems. They're sort of non-basic problems. They're good problems. But so I suggest on this homework for Wednesday, just focusing on these problems, the more basic problems from that 11.5 homework. So problems 1 to 4, I think those are about lines. And then 7 to 9 are basic problems about planes. And then problems 11 and 12 from the homework. Okay. And so the other problems I would, you can work on those. They're good problems, but they're a little bit more involved, maybe. They're still all problems about lines and planes and in 3 dimensions, but they may ask the questions in a different way. And so for the test, since we have limited amount of time to prepare for the test, I think you can wait on those. So I will adjust the due date on this to give you more time to work on these other problems. And so we will have time also to talk about them in class if we need to. But that doesn't mean that lines and planes are not on the test, right? So problems 1 to 4, and then 7 to 9, and 11, 12. Focus just on those for the time being, okay? To prepare for the test. Okay, who just came? All right, so I'm going to be back paper and a 3 index card. Two. Okay. Now, it's not a difficult question when I say if you just came in, raise your hand. Okay, so can you not respond to that, guys? All right. Let me go ahead and go ahead and pass out the sheet. And so again, make sure that you just focus on those problems, right, that are necessary for the test from that final homework. Okay. Let's dive in here quickly to the notes. All right, so that we can get as much experience as we can with especially with planes. We've talked about lines already. Okay, so so the key thing here is to give us more chance to talk about planes, and especially the sorts of problems that we're going to have to be able to do on the basic problems that we're going to have to be able to do on the exam, and the kind of basic problems that we'll see again through the semester. Okay, when we're using planes. So I have a little bit of recall practice for us here, just to remember, sort of basic facts about planes. All right, this is kind of the standard problem for planes, all right? And it's find the equation of a plane. Remember, that's going to be a single equation, right? Okay, that's going to be a single equation. So we want to find involving three variables, right? X, Y, and Z. So we want to find that single equation, right, for this plane that contains these 3 points. As long as you have 3 points that are not collinear, right? Okay, so they don't all fall on the same line, then you're going to have a single plane that contains a unique plane that contains those 3 points. So you should be able to write down the equation for it. Now, if you've got 3 points that are all fall on the same line, then there are infinitely many planes that are going to contain those 3 points, and so you won't be able to write down a unique equation for a plane, right? In that case, but these points are not collinear, right? And you can just see that intuitively because these points fall on axes, correct? This point, even without drawing it right, we can see from the coordinates, this point falls on the x-axis, right? This point is going to fall up over a little bit on the y-axis, right? And this one is going to fall up, right, on the z-axis. So there's no way, right, that those 3 points, I don't think, are going to be all on the same line, correct? So I think we've got a valid question here in finding this plane. All right, so let's remember the process, right? Because you're going to have to repeat this on the test. So again, here's a good thing to write down on your survival card. You got one in front of you, right? So you can scribble notes on this right here already, right? What is the basic process now for finding a plane that contains 3 points? What steps do we have to take? There are a few steps. They're easy steps, but you do have to go through the steps. Do you remember, Amber, what we do? What now? No, we don't need to find, unfortunately, we don't need to find any distances, but that is going to come up shortly, okay? Because a little bit later on in the class, you do want to be able to find the distance between a point and a plane, all right? So if we have a plane, imagine I'd like to be able to, in a moment here, find the distance between the point and the plane. Of course, there are a lot of distances between a point and a plane in different directions, right? Because, a plane is in, like, so yeah, approach the plane from many directions. But of course, we want the shortest distance between the point and, like, sort of the perpendicular. Right, but we're not there yet. Okay, yeah, Elijah, that's right. So exactly. So the key to writing down a formula for a plane is to find what's called the normal vector. That is the vector that's perpendicular to the plane. Okay. So remember, for a line in three-dimensional space, you need the direction vector. That's a vector that's parallel to the line. For a plane, it's just kind of the opposite, quote unquote. You need a vector that's perpendicular to the plane. Okay. So the way that's called the normal vector. The way you find the normal vector is you need then 2 vectors not parallel to one another that actually fall in the plane, all right? Or, vectors, of course, really don't have position, so it's really not fair to say a vector falls in the plane. But 2 vectors that you could put in the plane, 2 vectors that are parallel to the plane, okay? And that's easy to get, right, from the 3 points. All you have to do is create 2 vectors from 2 vectors from these 3 points, right? Okay, and those 2 vectors then will kind of fall in the plane, quote unquote, meaning that they'll be parallel to the plane, right? So, well, when you've got coordinates for points, right, it's so easy to write down. Vectors, right? So let's create the vector. First, let's create the vector that goes from this point on the x-axis, right, to this point on the y-axis. I'm going to call that u for lack of a better name. And then let's create also the vector there that goes from the point on the x-axis over to the point on the z-axis. And I'm going to call that v, just so that we'll have some a way to reference that, right? So u and v. You also could have figured out this vector that goes between these 2 points. We could have used that as well, but we don't need 3. Okay, 2 will suffice. So see if y'all can write down those 2 quickly there, those 2 vectors for me. You can write them down in IJK form. You can put them in component form in the 20 brackets if you like. Probably IJK form is may be preferable. Remember, that's called standard form, and the pointy bracket form is called component form, but they're really the same thing, right? Hi, man. I'm going to next card. That's worse. Okay, did y'all create those? So that should really be very quick, right? Okay. Um, on the test, you don't want to be spending a lot of time finding, the vector between 2 points, because then that will, not give you much time for doing the really more difficult things, right? What is this vector u? You can almost just read it off, right? Because the operations are simple. What? Yeah, minus 4i, and then what? Plus 3j. Oh, 0k. Okay. So no k component there, right? Okay. So you can write 0k if you want, or you can just leave that off. And then what's v going to be? Negative 4i, no j's, right? But plus 6k. All right. So these easy vectors. And so those two vectors now are parallel to the plane, or we can say they fall in the plane if we're thinking of them as connecting these points. And now from those two vectors that lay in the plane, how do we find the normal vector? So again, think of my hand there as being the plane. Have two vectors, right, that are in the plane. So think of finger vectors that we just created there in this plane. Okay, that is my hand. And I need a vector that's perpendicular to those two, right? Okay, that is going to be the normal vector for the plane, right? Now, so here's one of the fundamental facts, right? That we're going to repeat over and over again. Times. We're going to repeat it a few times right here in the class. If you've got two vectors and you want a vector perpendicular, those two vectors, what do you do? Yeah, that's one of the purposes of the cross product. So you really have to memorize that fact, right? So if you want to find that perpendicular normal vector, that's going to be the cross product of these two vectors. Okay. All right. So here's your chance to practice cross product again, but we've done this several times. So see if you can compute for me here the cross product of u and v. Once you've done that, then you're really in a basic problem like this one, you're really finished. Okay. It's really finding the normal vector that's really the key part to writing down the equation. Right? All right. Kind of like finding the direction vector is really the key part of writing down the equations for a line in 3 dimensions. So if you're not practiced with cross products, that have to get practice with that right before Wednesday. I don't think you should write. You don't want to write down the formula for the cross product on your survival part, because that formula is messy. There's a formula for cross products, right? You just want to remember the process of computing the cross product. All right, so y'all did that really well, so that's encouraging. So if I ask that several times on the test, you're going to get all those points. So what is that? What is that cross product there? It turns out to be. Does it start with an 18? 18i. If I write it in standard form, what plus? Is it plus? Plus 24j plus 12k. All right. So there's our normal vector or a normal vector. Any vector perpendicular to the plane, you can use as a normal vector, right? So there's one. And once you've got the normal vector right, then it's very easy to write down the formula for the plane, because you will use those the coefficients of the normal vector also as coefficients in the equation for the plane. So you would write 18 times x and then minus the x coordinate of one of the points here. All right. So let's use this first point since that's the first one in the list there. So you would write 18 times x minus 4, the x coordinate of this point, plus 24 times y minus the y coordinate of this point, which is 0. So, well, let's just write it down there formally, but you don't have to write minus 0. Plus 12, right? The coefficient of vector k, right? And multiply it times z minus the z coordinate of one of the points on the plane. All of that is just equal to 0. Okay. And then that's it. So if you're just asked for an equation for the plane, there it is, right? If you're not asked to simplify it. If we want to simplify this, let's do that. So we would have 18x minus 4 times 18 is 72, right? Plus 24y plus 12z is equal to 0. Let me take the minus 72 to the other side. So I get 18x plus 24y plus 12z is equal to 72. And we can reduce that a little bit. You don't have to, but you can make this look a little bit maybe neater or simpler by dividing these coefficients by the appropriate number, because all of these coefficients are divisible by 6, aren't they? So you can divide 6 into all of these terms in the equation, and you'll get 3x plus 4y plus 2z is equal to 72 divided by 6, which is 12. Oh, so there's a little bit maybe cleaner version of the equation for that line. Okay. But this if the question were just write down the equation for this, not line, but plane, right? That would be a satisfactory answer. The reason that I simplified it some there is because that plane happens to be the first example in the notes here, I think. Oh, there it is. Yeah. So the first example in the notes is something simpler than finding the simpler in a way, conceptually simpler maybe, but maybe not simple to execute. So we want to take that plane and we want to graph it. So we want to see if we can make a graph of this plane. And since that's a three-dimensional surface, three-dimensional surface, not easy to graph by hand, right? But if you're going to graph one, the plane is probably the one that you have the best shot at kind of making a clean graph of, right? So I'm going to show you how to do this, and then we're going to try the one on the And then we're going to try the one, I'm going to show you one way to do this. And then we're going to try the one on the sample test, okay? Because there's one on the sample test as well. Now, here's my suggestion for kind of a basic idea you can use to graph a plane and try to come up with a fairly decent looking graph. It's probably not going to be artistically beautiful, but something that's at least usable. Okay, so here's my idea. We're going to plot what are called the traces of this plane. Now, by the trace, I mean intersection of the plane of this plane with the three basic planes that are in your coordinate system, right? That would be the XY plane, which is horizontal here, right? And then that's the flat plane here, the XY plane. So that's your just familiar Cartesian rectangular coordinate system, right? So the intersection of the plane that we're dealing with here with this flat XY plane, that's called the trace of the plane in XY plane. Now, when two planes intersect, what sort of picture are you get? So if you have a plane, you intersect it, so pick up my hand plane, you intersect it with another plane, sort of thing, the intersection. It's going to be a straight line, right? Yeah, when two planes intersect, two flat surfaces intersect, right? You're going to get a straight line. So when this plane, whatever it was there, 3x plus 4y plus 2z equals 12, that intersects with flat xy plane, you're going to get a straight line that will lay in both planes. In particular, it will be in xy plane 2. So you'll get a straight line in the xy plane. Well, you're very familiar with straight lines in the xy plane, right? Okay, so that's nothing unfamiliar. However, other basic planes here in your three-dimensional coordinate system, you also have the YZ plane. So YZ plane is the plane that contains the y-axis and the z-axis, right? So the plane that contains both y-axis and the z-axis, that's going to be this plane that is kind of vertical here, right, in this picture, but is running from left to right here. Picture. I can go visualize that. So it's this flat plane that's that it's vertical, right? It's perpendicular to the xy plane, but it's running here from left to right because it contains all of the y-axis and also all of the z-axis as well, right? And that flat plane also will intersect with our plane 3x plus 4y plus 2z equals 12, right? And when those two planes intersect, again, you'll get a straight line. That's called the trace of this plane in the YZ. What's the third plane here? Sort of the third basic plane in my three-dimensional coordinate system. That's the XZ plane, right? So that's the plane that contains the x-axis and the z-axis. So that also is a vertical plane. That's a vertical plane in this picture, but it's running front to back here because it contains all of the x-axis and also all of the z-axis. Well, again, that xz plane intersects with this plane in a straight line. And that straight line is called the trace of this given plane in xz plane. So what we're going to try to do is figure out what those three traces are. Those are all straight lines. We're going to try to plot those straight lines. And then from that information, try to figure out, here's what the plane does look like. Because it's got to contain these three straight lines. Just right? Okay, let's start now by finding the easy one here. Well, they're all easy. They're all really the same. So let's start by finding what's the XY trace. So where does this given plane intersect with my favorite plane, right? The XY coordinate system, right? And so you do that by setting z equal to 0 in your equation. Because notice in the xy plane, right? The xy plane, Z coordinate 0, right? But you're flat in the XY plane. That means Z is 0 everywhere in the XY plane. So in this equation, just set Z equals 0. See what you get. Well, that's very easy, right? What do you get? Yeah, 3x plus 4y equals to 12. And then you just want to graph that straight line, okay? And you're good at graphing straight lines, right, in 2 dimensions. So this is just a straight line in 2 dimensions. So you can make this graph pretty easy. Actually, to make it really easy, let's just graph the intercepts. So I just want to graph the x and y intercepts of this line. So to graph the x-intercept, right, you set y to 0. Is that correct, right? So you would get 3x equals 12, or x is equal to what? 4. So x is equal to 4. I think that's right here. Okay. I think in this picture, positive x is in front. This is a first quadrant view. So positive x is in front, negative x is in back. All right. So and then the y-intercept. Well, we set x to 0. We get 4y equals 12. So that means y is equal to 3, right? So the y-intercept is right there for that line. And so you just have to connect these 2 points, right? And so we do that. I'm only going to connect between the intercepts. I'm not going to draw the whole line. Let's just connect between the intercepts here. But the actual trace itself extends, all the way across the plane, of course. Let's see, next let's try the YZ trace. So the YZ trace there looks like what? Set x to 0, right? So you get 4y plus 2z is equal to 12. And now again, so when you graph that, you're going to get a straight line. It's going to be a straight line in the YZ plane, right? So it's a straight line in the YZ plane, this vertical plane, right? That's running left to right. But again, let's just plot the intercepts, okay, to graph that straight line. So y-intercept, you set z to 0. Of course, you're going to get y equals 3 again. We already plotted that one. And when you set y to 0, get 2z equals 12. So that means z is equal to 6, right? Up here. So there is the z-intercept there. And then just connect these 2 points, right, with your straight line. And of course, let me scroll back up here. And now we can write down, of course, also the XZ trace, but you can already figure out what the XZ trace is going to look like, right? So the XZ trace just set y to 0. So you get 3x plus 2z is equal to 12. But when you graph that line, you're really just connecting these 2 intercepts. You get a straight line that's in the XZ plane, right? Which is this vertical plane that runs front to back. All right, so our given plane here, right, contains these 3 traces. So it contains this little triangle. So you can shade that kind of, and so there's a piece there of your there's a little piece there of the plane. Of course, it extends infinitely, right? Front and back and left and right and so there. But there's the piece of the plane that's above, like it's above the quadrant. So that's the part above. It's not really a bad picture, right? Of at least that little triangular wedge, right? Of that big plane. So there's a way there of graphing planes. Now, unfortunately, it doesn't. This system breaks down in certain cases. I'm going to show you a couple more examples here in just a minute where things can go awry. All right. So because some planes are a little bit simplified, and when you try graphing the traces, you end up not having all the traces, and so you have to sort of figure out what the plane looks like without the traces. If you think about it, usually you can figure it out, but sometimes it does require some extra thought. All right, so let's look now on the sample test. Okay, and there's one on the sample test, and it's this one. Oh, so the picture's already drawn there. So, but I'm gonna let y'all draw the picture, and let me cover up these answers here also. So there's the question right there at the bottom of the screen, if I can get it on there right. See if I can scroll on this thing. Now, some of it you can see, all right, but this is easy, all right. So there's a plane, right? That's a little bit different from the one we just dealt with. I think it's not the same one, not is it? Okay. And so we want to graph this one. So you want to find the three traces, find the equations for the three traces, starting with the xy trace. So there's the xy trace. That's very easy, right? Just plug in the 0 for the missing variable, and you'll get an equation with two variables then, right? That, of course, is going to be a straight line. And then plot those traces, at least between their intercepts. May not want to plot the whole trace, but at least between the intercepts, plot those traces, those three traces, and then see if you can connect those to get a graph. All right, so try that on the graphing paper that I gave you. Everyone get a piece of graphing paper there. So I think that graphing paper is just like the image that we were just drawing on a moment ago. This is a first quadrant view. So you got the positive part of the y-axis going to the right there, and the positive part of the x-axis is coming towards you in front. Okay, so we have a first quadrant perspective on this three-dimensional coordinate system. If you can plot those traces and see what effect. So, okay. Yeah, so 2x minus 6y plus 3z. Just write down the three traces, find your intercepts, and plot them. See if you get a little triangular edge piece of that. Don't peek at the answers on the answer key. Don't peek at the answer. Doing this. All right. Let me peek though. Cheat. So that picture is going to end up. I should have drawn from a different perspective, but that's fine. Okay. See it? Yes. Yeah, on the answer sheet, I have a different perspective. This just illustrates. All right. This illustrates the issue with perspective. Yeah, here. Tiny wedges that. Yeah, that's right. That's what the angle. Yeah, that's what sort of. Yeah, I think you're in the wrong quadrant, but actually it helps you from that picture. Y'all give it a really good, I'm giving it a very helps try. That's an awkward picture. But unfortunately, it'd be nice if we software you say nice if you don't have a good view. You can rotate your axis so you can see um, a better view. All right, so y'all did everyone I saw there that was finished did that very well. So there are the traces. So everyone must have got the traces right. And so on the answer key though, it's a little bit easier because we have a different perspective. All right. So on the answer key, this is the negative part of my axis. This is still the positive part of the x-axis. So this is a fourth quadrant perspective, and that gives you a better, that gives you a sure. Right. So the intercepts were what? -2 on the y-axis, right? And 6 on the x-axis, or on the z-axis, right? So there are the traces, and so we try to shade in that surface that contains the traces. Yeah, from this perspective, something like this, but from first dimensional perspective, the way had the axes tilted there, it's really awkward. It's like just like you're staring right at the right? Okay, so you really don't even get a surface. So I think I can do that on the test. Well, it gets a little bit uglier, unfortunately. So if in other certain cases, let's look at this one. So this is the this is in 3 dimensions. That in 3 dimensions, right? That's the indeed that's the equation for a plane. Okay, it's just that this first term, right, is missing because it has coefficient 0, right? So you have 0x plus y plus 5z, right? And that's going to make the graph a little bit harder to. That's going to make the graph a little bit harder to understand. By the way, what is the normal vector? What is the normal vector for this plane? So if I did ask that, not the, because normal vectors are not unique, but what is a normal vector for this plane? What could you say there? What now? Yeah, 0i, right, plus, yeah, 1j or j, right, plus 5k, correct? Right, okay. So, in other words, just j plus 5k, right? So, so that vector is perpendicular to whatever plane here we end up graphing, right? Now, so the thing that messes stuff up here are the traces are a little bit hard to understand. So if you try to find the YZ trace, that one is pretty normal. Okay, I shouldn't use the word normal. That's pretty much what what you would expect. Remember, you're just going to set x to 0, right? And so you get y plus 5z is equal to 10, right? And so you can plot that easily, I think. Let's see if we can. So I don't know if we can get it all on. Problem is getting all of that on the screen at the same time, right? So I want to graph y plus 5z. So if z is 0, y is 10, right? And if y is 0, z is 2. So it looks like we have a y-intercept of 10, all right? And then a z-intercept up here of 2, right? Okay. So if you connect those, you get, this line, right? So that line, which is in the YZ plane, so that line is in the YZ plane, right? That's going to be part of your, that line is part of it. But where things get a little bit less easy to understand in this example are the other traces, unfortunately, okay? So, because if you try to find the other traces, things start acting weird, right? So if you try to find the, for instance, the y trace here, right? I'm sorry, the xy trace here, right? What happens? So you just set z to 0, correct? And you get what? Y equals 10. Okay. So now that is a line, okay? But what does that line look like? See, that's a constant, right? And when you graph that constant, you get a picture like this. You just get y equals 10, see? If you graph that in 2 dimensions, you would say that's a horizontal, you would say that's a horizontal line, okay? But it looks a little bit different, right? Okay. So see, things are going astray here already for us there, right? Okay. So, but we do have to think about that now. I'm trying to construct the graph. So what that's telling us is this plane, right? Okay. When we plot it, this plane contains this line, right? But when it intersects the xy plane, you just get this this line. This y equals 6. So I think we already have a picture of this in our mind, right? What's this plane going to look like? I think it's going to, so it's going to slice through X line right here, right? But it's got to contain this line. So that means it's tilted up, right? Slightly. It's coming up here to the, across the Z axis right here. So it's kind of like the XY plane, but it's just been tilted. Okay? Across the Z axis right here. Now, if that is indeed what the plane is, right? But we just have sort of the XY plane tilted up, right? So that it contains this line. Then guess what? That plane will never touch the x-axis. Will it? It's going to totally miss the x-axis. But is that what the equations tell us? I think that is right. Because if you try to find, for instance, the xz trace here, right? So if you try to find the xz trace, what does that look like? Yeah, it's 5z equals 10, right? Which means what? Z is equal to 2? Ah, so you get z is equal to 2, or you get this line, right? Is that right? This line, z is equal to 2? Remember, this is in the xz plane, right? In the xz plane, you get z is equal to 2. So in the xz plane, right, that moves forward and backward, you get this straight line. Oh, I think that's what we expected, right? Okay. this plane comes up, right? Okay, and so when it hits the XZ plane, it's going to just slice it right there at z equals 2, but it's never going to touch the x-axis. Never. Wow, can we draw a picture of this now? Maybe sort of. Can we put some other edges? Can we put some other edges on it? Let's see. Let me extend this out. Let me extend this picture out. I'm trying to draw this. I'm trying to duplicate this line over here on the top. So does that, well, that kind of looks like it, right? Okay. And then let's try to do the same thing in front. Let's see if I can do it in front. Does that give the illusion of coming up? Maybe if I cut off some of this front part of this line. Oh, yeah, well, kind of. All right, so I can live with that. Right. I don't know if adding any shading in here would help or not. Probably just make it worse, right? So there's that. So tossing slide. See, well, that takes a little bit. So they're not even for planes. They're not always easy to. They're not always easy to graph. By the way, this type of plane, this is called a cylinder. Now you may wonder, that doesn't look anything like a cylinder, right? What we think of as a cylinder, but this is called a cylinder because all it is that line, that YZ trace. Notice all you've done is to form this surface. All you've done is taken that line and moved it the front and to the back, right? Okay, that whole surface is nothing but that line just swept forward and swept backwards. That's the whole surface. You can create a surface like that by taking a curve and moving it in some direction, up or down, left or right, or at an angle. That type of surface is called a cylinder. The reason it's called a cylinder is that's how you create cylinders. A cylinder is nothing but a circle, right? That has been moved up, right? To form a surface. So you see, if you take a circle in the XY plane and just think of moving that circle up, right? Vertically up to sweep out a surface, get a cylinder. Well, this surface is formed the same way, except you don't take a circle, you take a straight line. But any surface formed like that from a single curve, just moving a single curve space, that's called a cylinder. All right. This one is easy if you think about it just right. So see, this one's a greatly simplified. This is still that's still the formula for a plane. The normal vector is nothing but 2k, right? So you have a very simple normal vector here, just 2k. So 2k is a perpendicular vector, right? It's going straight up and down. It's perpendicular to the xy plane because it doesn't have any I component or j component. So it just goes parallel to the z-axis. It just goes straight up and down. That is the normal vector, though. So that means that the plane itself has to be perpendicular to this vertical vector. So if it's perpendicular to a vertical vector, that means it's flat, right? So our plane here is just going to be a flat plane in 3 dimensions. Well, what flat plane will it be? Well, look at the equation here. If you solve this equation for z, you get what? Z is equal to 5/2. So what that's telling you is z is constant. Z is always 5 halves, okay? X and Y can be anything, but Z is 5 halves. So when you plot this, you get a flat plane, but it cuts through, instead of cutting through Z equals 0 like the XY plane, it cuts through Z equals 5 halves. So it's just the XY plane has been elevated up to Z equal 5 halves, right? That's what, just take the XY plane, shift up 5 halves on the Z axis, get the Z equal 5 halves, okay? How do we call that? Gosh, I have no idea. So it's going to look like the XY plane, right, has just been shifted up by 5. Going to be shifted up by 5 halves. See, if I shift up by 5 halves, that's about that distance, right? So draw a line here. And it's not going to look like it, is it? So it's a, well, I could have done worse. All right. So just taking the XY plane, moving it up by 5 halves. I don't know how to show in the picture. I need some help. Maybe I don't know how to show in the picture that that plane is cutting Z equals 5 halves. Okay. I do sort of have the illusion that the plane has been elevated, right? But exactly 5 halves.
X, Y,
Mm-hmm.
higher, but you have to 10 as if
Oh, I see. Yeah, so have a cross hatch there that goes to 5 halves. That's says add some extra dash lines there on your elevated plane, have them intersect by 5 halves. That plane. Okay. All right. So there is just a little bit on the test of graphing planes, but I think I think you'll be able to plot the traces if I get the right if I get the right set of axes on the test from the right perspective. I think you'll get a decent picture of the problems on the planes on the test, just using the trace method. Now, one other. There's several different sorts of problems that we can solve with planes and lines, but one that I want to get to first, I'm going to skip a little bit in the notes here to make sure that we get a chance to talk about this one. Then we'll come back to some of the more exotic problems, which are in the homework, but not on the test. All right. So one thing we want to be able to do in 3 dimensions is find distances between planes and okay. And so I mentioned the problem earlier. I want to be able to find the distance between, in particular, between plane and a plane. Okay. So shortest distance between. And then, but you can pose lots of questions like this. So you might ask, can I find the shortest distance between 2 lines? Okay. If I have 2 separate lines in 3 dimensions, how do I find the shortest distance between the 2 lines? Or if I have 2 parallel planes, parallel to each other, how could I find the shortest distance between the 2 parallel planes? If the planes are not parallel, of course, there is no distance between them, right? Because they'll intersect each other, all right? But if you have parallel planes, they might be tilted, but they don't have to be flat. If you have parallel planes, how can we compute the shortest distance between parallel planes? Questions like that. But let's start with the easiest question. How do we find the distance from a point to a plane? That sounds like a calculus problem, and in a way it is, but we don't have to solve it with calculus because it turns out that our vector operations are really powerful, and they're going to allow us to solve this problem without knowing anything about calculus in 3 dimensions. All right, so let me draw a picture here of this situation. So this picture comes from the book. So here I have a plane, right? That's pretty obvious. Right here is this plane, and here's a point in the plane. Okay, so we're going to call that P. So P is not the name of the plane. P is the point that's in the plane. So you can see the plane drawn here. So they've drawn the plane like it's flat. All right, but it doesn't have to be flat like that. All right, and then we have some other point that is not in the plane. Obviously, you don't want a second point in the plane, right? Because then the distance from that point to the plane is 0, right? So you have some other point not in the plane. By the way, if you're given a point, right, and you want to test if it is in a plane or not, what do you do? So how can you figure out, for instance, that this point Q is not in this plane? Even easier than cross product, Elijah. Yeah. Yeah, you just insert it. You insert the coordinates in the equation, right, for the plane. So assuming that we have the equation for the plane, just insert the coordinates of the point into the plane, and if they satisfy the equation, then that point is in the plane, right? If they don't satisfy the equation, that point's not in the plane, right? So it's just a very simple algebra. We don't have to do anything fancy in that case. All right. So here we have this point Q not in the plane, and I'm trying to find the distance from this point Q to the plane. Well, of course, there are lots of distances from the point Q to the plane, right? Okay, if you go in different directions, you'll get a different distance from the point Q to the plane. Of course, I'm looking for the shortest distance from the point to the plane. So kind of the perpendicular, what's the perpendicular distance, so to speak, from this point Q down to the plane, right? But we're given a point, or at least we can find a point P that's in the plane, right? But there's no guarantee that this point is directly beneath the point Q, right? This distance from P to Q may not be the shortest distance. I'm looking for the shortest distance here, right? Which is this distance D in the picture. So the question is, how can I do that without knowing calculus? Okay, without knowing calculus, how can I do that? Well, here's the answer. So you just have to remember about vector operations. Right now, this being a plane, right? You're going to know, hopefully, right? You will know the normal vector. You will know the normal vector for the plane, right? Remember, the normal vector is perpendicular to the plane, just like is shown in this picture. Okay. Now, of course, that normal vector can be any length, right? That normal vector can be any length. So it could be short, it could be long, right? But you will know here this normal vector. If you're not given it, you can read it off the equation, right? You know how to read the normal vector off the equation. Now, find the vector then. Find the vector that connects a point in the plane to this given point Q. Remember, you have to be given this point Q because the purpose of the question is to find the distance from Q to the plane. So the point Q has to be given to you. The point P may also be given to you, or you may have to discover this point P, any point in the plane. You may have to find a point in the plane. Of course, how do you find a point in the plane? Well, you just have to find a point whose coordinates satisfy the equation, right? Okay, so you just do that by inspection or a little bit of experimentation. Find for a point the plane, right? Okay, so form the vector, right, from the point in the plane that you discover to your given point Q. Okay, so if in this picture, that would be the vector PQ, right? If we don't want to give it a shorter, name, there's the vector Q. Now, of course, you can compute the magnitude of this vector if you want to, right? But that magnitude is probably not what you're looking for, correct? Because you want the shortest distance from Q down to the plane. So unless you're really lucky, you won't have picked this point properly, right? The distance from this point to Q won't be the shortest distance, right? You want the perpendicular distance from Q down to the plane. How do we find that perpendicular distance? Okay, well, look, you can kind of see how you're going to form it. You can kind of see how you would form it from this picture, right? From this vector PQ, start drawing lines here that are perpendicular to your normal vector. Am I drawing those lines properly? So you want to draw these lines that are perpendicular to your vector PQ, that are perpendicular to the normal vector, right? And then you'd like to stop here, of course, you know, when you reach the end of the vector PQ, all right? So that's this distance, which corresponds to the shortest distance, correct? But look, notice that when you draw these perpendicular lines, what you're creating here is another vector, a vector that falls along the normal vector, right? But may not have the same length as the normal vector. What do you call this vector here that we've just created? That's the projection, right? So remember computing projections? That's exactly what we've done here. We've created a projection. In fact, we've created a projection of this vector PQ onto the normal vector. That's what we've done. So it's just a matter of finding this projection. It's the projection of this vector Q. Right. So it's the projection of this vector onto normal vector, and we know the normal vector. Right. So this calculation, and then compute the magnitude of this vector. You gotta find the magnitude. Find the magnitude of this vector. That's perpendicular. Because the magnitude of this vector says this, like you straight down to. Right. So that's indicated here, right in the picture. There's the formula. So it's not that hard at all. No calculus involved. That's a miracle. No calculus involved. Usually, you know, when you're in calculus 2 and you're looking for shortest distances, right, between things, you often have to. That often ends up being a calculus problem. It involves differentiation, right? But here we don't have to use any calculus. We can put just vector operations. So that distance, here's a formula for you. Say for right. Yep. So the projection onto the normal vector, like this vector. What's the vector? That's the vector between any a point on the plane, any point on the plane, and then what you were asked about. This point. Questions? What's this given point? And here's how you compute that. Okay. So that's the simplified magnitude of projection. Here's how you compute a projection. But remember, a projection is a vector. You want the magnitude. Oh, so it turns out when you magnitude is just the absolute value of this. This is the dot product. It's the absolute value of this dot product divided by magnitude. But if you don't remember that formula, just remember how to compute a projection. You'll need to remember this anyway. And then just take the magnitude. Okay? It turns out in this case, it's simple. Simple. Capitalized. The magnitude. It's absolute value of the dot product because the dot product is a number, so it doesn't have a magnitude. but absolute value is kind of like magnitude of a number, right? But the dot product can turn out to be negative, so that's so you're going to end up with a negative distance, which of course you don't want, right? So that's why you put absolute value on top of it. Well, let's see if that works. Now I love this one because it says graph the scenario here. Well, while y'all are computing the distance, I'll try graphing this I'll try graphing this picture. All right. All right, so let me see if I can get everything on there at once. So there we go. All right. So this is just a very standard typical problem like you might be asked on a test. So some of the problems in the homework, the ones that I omitted, they're a little bit more exotic than this. So they may ask you the distance between a point and a plane, but they may ask it in kind of a roundabout way or with unusual information that you have to somehow think about. Okay, but this is just a very straight problem. You want to find the distance between this point and this plane, right? There's the but remember, must find a point on the plane, okay? Right? Must have a point on the plane because you need that point find the vector to that given. This is point Q. This is point Q. And you need to find that point that is on the plane. So how do you find a point on the plane? Really fast way. Right. Yeah, just set a couple of the variables to any values you want and solve for the third variable. Okay, so if you wanted to set x and z, x and y to 0, and then solve for z. So you would have 0, 0, and then that so 0, 0. Okay. But you could use that point, or you could set x and y to anything and solve for z, or set y and z, or x and y solve for the easy to find a point. Like, let's check. But I hope this point is not on the plane. This point is on the plane that ruins the problem, right? Yeah, plug it in, right? So you would have 20. That's already plus 12, which is already 32, right? And plus 3, 35, right? Which is certainly not equal. So this point is not on. So that point's not on the plane. So let's find that the distance from that point to the plane. All right. So try using that formula really fast, right? Okay. So it's really pretty fast there. You have to find the normal vector and compute the magnitude of the normal vector. That's a little bit messy, but not too bad. All right. So I'm going to scroll up here because I'm going to see if I can draw the picture while y'all are contemplating that. So y'all have that formula written down? Another terrible. Another terrible plane here. Wow, that's cannot figure that out at all. Some distance like this, but that's yeah, that's not okay. Did y'all what did y'all get for? So we probably all wrote down the normal vector the same, right? So what's the normal vector there for that plane? Yeah, 2i minus 6j plus 3k, right? And then what did the magnitude of that turn out to be? Because we need that in our formula there. Oh, is it exactly 7? Yeah, that's oh, perfect, right? So it's 7. Oh, great. Okay. So that's 7. And now, of course, this dot product now, you may have different because, or you may have computed that differently because it depends on what point you chose for P, right? Okay, the point on the plane, and you could choose different points for the point on the plane, and then that would give you different vectors, right? So, but anyway, did you end up with a distance here? See if we got some agreement there. So did you end up with a total distance there from that? Um, you got 5? Someone else get 5? So we ended up with 5/7. Oh, oh, all right. So you got 35/7, which reduced to what? 5? Is that, oh, so you got 5 altogether there, Elijah? Oh, yeah. Okay, so that sounds like that's probably the right answer. So see if you didn't finish, see if you can eventually there come to 5, right? So we get that's unbelievable. We got a nice distance there. Okay, exactly 5. They almost always involve square roots, right? But this one turned out to be exactly 5. I think I just guessed at this. I think I just guessed at this point also. So that's even more miraculous that it came out to be exactly 5. Um, the picture is terrible, so because of again, I got the wrong perspective there. So, so there's the plane and the point's over here, but trying to figure out how that point relates to that plane is really hard. Okay. So I gave up on drawing a nice picture from different perspectives. You can get a better idea of that distance between the point and this plane. Gosh, yeah, this is really hard to think about. How does the plane come down like this? So I don't know. Okay, it's really hard to imagine that distance from that point to the plane. All right, so there's one like this on the sample test. Maybe this is this. I don't think it's the same problem. So if we look at the sample test, there's a very straightforward problem like this. Problem number 11. Okay. Oh, this one's very straightforward, right? So there you're given 2, and it's the so there you don't even have to find the point out. Oh no, you do have to find the point. Okay, and you're given the you want big difference. And I think that's fine. Like oh. So vector right, total vector still so vector sets. All right, so there is there for sure, right, is another formula, right, that that you'll want to include on your survival card. But remember that comes from the projection formula, right? Okay, so you'll need to have the projection. Also, you may be asked projections, other contexts, right? Projections are useful. So, countable distance. So, projection formula. Projection is a vector answer. So it's going to have 3. All right, now there's no problem like this on the like the ones I'm getting ready to show you now on the sample test. So there won't be a problem like this on the test, but this is in the hole, okay? But this does not involve distance. It again seems like a very complicated problem, but our vector operations really make this all right. So suppose you've got 2 planes, right? And you want to find the angle between 2 planes. Okay, so remember we talked about finding the angle between vectors. Now we want to find between 2 planes, right? So you have 2 non-parallel planes, because they're going to cross each other at an angle, right? And so how do we determine that? Well, the answer is very easy, because the angle between the planes will be the same as the angle between their 2 normal vectors. All right. So here's a little picture that illustrates that. So here we've got these 2 planes, right? Of course, they could be perpendicular, in this case, the angle between them is going to be 90, right? But let's so I guess they can be 90, but make it an interesting picture. So the thing is not 90, right? So here we have between these 2 planes, right? And but if you can see just from your geometry intuition, right, that look at the 2 normal vectors for the planes, right? The N2 is the normal vector for this flat plane, because N2 is perpendicular to the flat plane. Right? Then one N1 here is the normal vector tilted plane here. One. Well, notice that the angle between two normal vectors, as they are perpendicular to the planes, be the same as the between the two. So angle between two planes is really the same problem as finding angle between two vectors, right? But in this case, it's just the two. So if you know how to find the angle between two vectors, find it between two planes as well, just as easily. So there's another formula, though, right, to remember. Okay, so there's the formula for that you can use. It's not really the formula for the angle between two vectors, right? But there's the formula you can use to find the angle between two vectors. So it's the dot product of the vectors, right, divided by the product. That gives you the cosine of it. And then we just use our cosine effect. So, by the way, when two planes cross each other, right? They really form two angles, don't they? They'll form an acute angle, right? But they'll also form a larger angle as well, right? So this formula is going to give you one of the other. Well, it will give you the one that's between 0 and 180 degrees. Okay. Let's try. Let's just try this now, just for a little bit of practice. Again, mostly with just our here, right? Yeah, so let's find the angle between these two planes. I have no idea what this looks like. I'm not going to try to graph those. Okay. So let's see if we can do that. So what's the steps? Very easily, right? You need to first pick off what? Yeah, you need to read off the normal vectors, right? And that's the easiest thing to do, right? Because it's just the coefficients of your variables. So your normal vector for the first one is what? 2i minus 4j plus 3z, right? And then for the second one, it's what? I plus 2j plus, not z here, but k, right? Plus k, right? Is your second normal vector. And then you're just going to plug those things into the formulas. So you have to compute some magnitudes, right? That's the kind of the icky part here. So you have to compute the magnitudes of those vectors, and then also the dot product, right? So you'll want to compute the dot product of those two things. That's easy. And then, of course, you'll need your calculator to compute an arc cosine, right? So try calculating those just to give you a little bit more arithmetic practice. Probably the last thing you need, right? Okay. But it does help to at least execute the formulas. Even if it's just arithmetic, it helps you remember the formula, right? So remember, there's the formula for the cosine. Right now, it's fine with, right, but most of the time we've been saying. There are many times though where Now, one thing I do want to caution you about on the exam is showing your work. So when you do come to take the exam, you will need to show work. So be prepared for that. Right? Everyone, so here. I'll remind you of that. I'll remind you of that on Wednesday, but be thinking about that in the meantime. I have to show it. I have to be showing. Doesn't mean as much. It does not mean as much detail as I go into on the sample. Don't think that I have to show every single step like I tried to do on the sample because I was trying to make that easier to take steps, right? But you do have to show enough work that I can see. Now, there's no restriction. Okay, so let's try to fill in some numbers here, right? So, what is the magnitude of N1? What does that turn out to be there? Almost can do it. Is it 20 square root of 29? Is that it? So square root of 29, and then for N2, obviously square root of something, right? 6. All right, and neither one of those are going to simplify. Okay, so can't simplify at all. Maybe that's good. And then the dot product of the two. What does that turn out to be? What now? -3. Okay. All right. So we end up here with -3 over is it -3? Yeah. Over the square root of 29 times the square root of 6. And there's really no reason to simplify that by hand. Just might as well jump right straight to our decimal approximation, which is what? Negative something there, right? Pretty small number. So negative 0.2274, or about 0.23 if I round off. Is that close? All right, so minus 0.23, and then we want the arc cosine of that, right? So our angle is approximately whatever the arc cosine of this is. So what does it work out to be? Here we're going to get the larger angle between those two. What is that? 103? And I guess if you subtract that from 180, that would give you the smaller angle between those two planes. Okay. Okay, so that's pretty easy, right? It's just a matter of remembering that formula. So see, these vector operations, they really are quite powerful, right? Let me see what this question is. I think we won't do this one yet. We'll save this for next time. But this one also is pretty easy. What we're trying to find here is the intersection of two planes. So if two planes are not parallel, right, they're going to intersect in a straight line, as demonstrated in that picture, right? So when two planes, non-parallel planes intersect, that you get a straight line. So the point here is to find out what are the equations for that straight line where two planes intersect each other, right? Okay. So that also turns out to be very straightforward, just using our vector operations, except it's a little bit messy in the sense that, you know, equations for lines in 3 dimensions are messy, right? So you end up with, of course, the 3 equations for the straight line in 3 dimensions. So that makes it a little bit messy, but conceptually it's easy, all right, to do. But there's not a question like that on the test. So we'll save that one for Monday. Let's save that for Monday. So that we don't get overloaded here on things that we have to remember for Wednesday. Okay. Do y'all have any quick questions? We'll probably have about 15 minutes that you can ask things if you need to before the test on Wednesday. We have enough time, I think, where you can ask some quick questions on Wednesday before the test if anything's bothering you. So we'll have that little piece, but anything else today? No. Yeah, I know. You need the survival card. Well, that's optional. The calculator, I guess that's optional, but you better bring that. And or otherwise, I think you have a hard time computing arc cosine, for instance, right? And then something to write with. That's it. So the paper, I supply that, so you don't have to. Yeah. Okay. What now? What? In color? Try to avoid like orange. That will blind you. Other than that, okay. Please remember though, do bring something to write with it. Right? I'm trying to say and in words of life, I think fill out your survival card and bring that. That's bound to help you, but so that's optional. Some people can memorize these things. Please don't. You feel like you don't need that, then that's fine too. Okay. So I'll see you guys on Wednesday. Bye.